US Physics Olympiad, year 2020, USAPHO, final round. Problem A2. Swoosh. In 1851, Leon Foucault built a pendulum 67 meters tall with a 28 kilogram weight. He connected it to the top of the Pantheon in Paris with a bearing that enabled it to freely change its plane of oscillation. Because of the Earth's rotation, the plane of oscillation smoothly moved over time. If we imagine a large horizontal clock under the pendulum, if initially the oscillation went from 12 to 6, later on they would move to the 3-9 plane, for example, as shown in the figure below. Perhaps surprisingly, the time it took the oscillation to go back to the original plane is longer than 12 hours. In this problem we will investigate why this is the case and what the shape the pendulum traces out. Figure 1. Left. A schematic of Foucault's pendulum. Right. The pendulum motion projected on a horizontal plane in the rotating lap frame. First, consider the case of a Foucault pendulum installed precisely at the North Pole with the length L. We denote square root from G over L equal omega. The angular velocity of the Earth is capital Omega. John is an observer looking at the pendulum from a fixed point in space. At t equals 0, he sees the pendulum at position A0 and with the velocity 0v in the xy horizontal plane. Question A. For John, what are the approximate equations that describe the motion of the pendulum in the xy plane? You may assume that the amplitude of the oscillations is small. We define the coordinates of the pendulum at rest as 0, 0. Question B. What will the coordinates x, y in John's frame be at a later time t? Question C. Ella, an observer, resides at the North Pole, is also looking at the pendulum. What are the coordinates x tilde and y tilde as observed by Ella? Assume that at time t equals 0, the coordinate system of John's and Ella's overlap. Question D. What is the speed of the pendulum bob observed by Ella at t equals 0? Question E. Find the initial coordinates for A, V such that as measured in Ella's frame. Case 1. The pendulum passes precisely through its resting position. Case 2. It has a spike at the points of maximal amplitude, see figure below, instead of a rounded trajectory. Figure 2. Two possible trajectories with a spike, left, and more rounded, right. In a rotating frame, a fictitious force known as the Coriolis force acts on the particles. For Foucault's pendulum, the Coriolis force acts primarily in the horizontal plane in a direction perpendicular to the velocity of the mass in the Earth's frame with magnitude F equal 2m big omega v sine theta, where m and v are the pendulum's mass and its velocity, and the theta the latitude, 90 degrees for the North Pole. Note that when the velocity changes sign, so does the Coriolis force. Question F. how long would it take for the plane of oscillation of Foucault's pendulum to return to its initial value in Paris, which has a latitude of about 49 degrees.